Commercial, good quality, high frequency active probes can be very expensive. Reason why I decided to make my own. Here are the schematics of the probes. This circuit here is based on the BF998 MOSFET, and you can find related videos on the internet. It was discontinued, but we still can find them on the market. I particularly bought from eBay, and despite comments I read, mine are legit. The second circuit here is mine, and it's just a resistive divider followed by a 20 dB low noise amplifier, the Gali 39 from many circuits. Basically, it's a simple 10-to-1 divider followed by a 10 times voltage amplifier. So an innocent 1-to-1 probe. But in real life we know that high frequencies and high impedances don't get along, and pins and ground clips add parasitic capacitances and inductances, as we'll see in a while. And this is the setup used to evaluate the probes. I installed a SMA connector here, and in this case I used the output connect directly to the oscilloscope. This probe is the Gali 39 one. And for other probe, I had to use this amplifier here to boost the signal, as the probe doesn't have an internal amplifier. Consider what we just saw as an intermediate test of the probes to evaluate their performances. I certainly knew that the final performance would change significantly after encapsulating in the final enclosure, as we will see in a moment. The front end of commercial active probes is normally specified as a large resistance, 1 megohm for instance, in parallel with a small capacitance, as in the SAP 2500 from Sigland, rated for 2.5 gigahertz. Notice that the resistive part is basically the resistance for very low frequencies. The test of my open probes with connectors shows the same behavior as we can see in this table here. This is the impedance measured with the network analyzer, and we can clearly see that the reactive part, capacitive, is predominant. This other column shows the magnitude of the impedance, and these two columns here show the equivalent parallel impedance, and the reactive part, which is a capacitance, have an average value of 1.3 pF. The exactly same tests were done in the BF998 probe, and the result is very close, as we can see here, 1.5 pF. This is the setup I will be using to measure the performance of the probes in their final forms. There is a through SMA adapter at the end of the cable, and the VNA was calibrated from 20 MHz to 1.1 GHz with a male calibration kit. I will also be using this adapter I made for the probe tips, and it's just ground mass with a 0.5 millimeter hole to accommodate the ground clip. There's also a small screw here to hold the ground wire and make things easier for me. Let me zoom in. The termination is open, as you can see here, and now I will include the adapter. You can clearly see that it didn't change anything. Now I show what your circuit will see when you use the probes. For this test I will use the BF998 and Gallium-39 probes up to 1.1 GHz, and also the MHO98 oscilloscope probe, the RP3500A, up to 500 MHz, just to compare with the other two. The VNA is already calibrated. Let's start with the BF998 probe. You can see the impedances here. I set markers for 50 MHz, 500 MHz and 1 GHz. Now let's check the magnitude. 1.65 kilo ohms for 50 megahertz, 211 and 90. This is the Gallium-39 probe. Let me change the marker to magnitude. And here we go, 422 ohms for 50 megahertz, to 241 for 500 and 120 for 1 gigahertz. And here we can see the behavior of the Sigland probe. As I said before, this is a 500 megahertz probe, so the maximum frequency is 500 megahertz. Now the magnitude. At this point one could say, why bother using the scope probe if the homemade ones are better? The answer is simple. The original probe can withstand up to 300 volts RMS. This is almost 850 volts peak to peak, and are very good for low frequencies, being able to measure DC voltage as well. Now let's measure the performance of the probes in these controlled conditions. The RF generator is terminated with the 50 ohm through load, and at the oscilloscope input there is a 6 dB attenuator. The internal termination is set to 50 ohms and the probe setting is 2 times due to the attenuation. The output of the homemade probes is connected to the scope with RG316 coaxial cable having a length of 215 centimeters or 85 inches. The measurements will be tabulated and I will show the result next. Let's start with the Galli 39 probe. Let me zoom in. Starting with 10 megahertz, you can read the voltage peak to peak here, the average, and the frequency here. .1 gigahertz. It's the BW of the scope. Now let's replace the probe. For the BF998 probe, I had to use this 20 dB low noise amplifier, as this probe has a high input attenuation and does have an internal amplifier. 10 megahertz, bit noisy, the level is not high. $20. $100. 110, 100, 200, 3, 4, 6, 700, 800, 900. Okay, it's clear that with this probe we can't go past 800 megahertz. For the Siglent probe, I changed the setting to high impedance and change the probe to 10 times. Let me zoom in. Okay, 10 megahertz. 50. And 50, 200, 300, 400, 500, 6, 70, 80, 500. And here is the final results of the tests. This yellow line here is the response of the 1 GHz oscilloscope directly connected to the RF generator with a coaxial cable, and we can see that's pretty flat. The gray line is the response of the scope plus the Rigo 500 MHz probe. Notice the bump here at 500 MHz. The orange line refers to the BF998 probe, which was discarded. And finally, the blue line, the response of the Gali-39 probe, including the 215 centimeters of RG316 coaxial cable, which had a performance better than I expected. As we just saw, many active probes are not that great on the y-axis. In this signal specification, for example, the attenuation ratio is guaranteed just for very low frequencies, as you can see here. This means that we must be sure that the probe will be good on the x-axis, otherwise the probe will be just useless. So we must be sure that we are not loading our circuit, causing distortions. To check the performance of the probe, I'm gonna use this function generator over here with a square wave of 80 MHz, the maximum this generator can go. First, I will connect the generator directly to the scope and check the shape of the wave and the rise time. You can see here that the rise time is 1.66 nanoseconds. Now I will load the generator with through 50 ohms load and connect the probe, measuring the rise time again. 1.6566 nanoseconds. Not bad. And here the overall specification of the probe. Notice that the maximum input voltage is 1.26 volts peak to peak. This is the maximum level before the amplifier starts to compress its output. This could be higher, for instance 6.3 volts peak to peak, if you replace the resistive divider at the input, so to have a 5-to-1 probe. We can see here that it's pretty robust. The damage level is 28 volts peak to peak at the input. The power can be connected to any USB port available on the workbench, which is very convenient. Finally, let's have an idea how far this probe can go. Unfortunately, I don't have any scope with a BW greater than 1 GHz. Then I'm gonna use the spectrum analyzer for that. The probe is connected to the RF generator via a to load. 1 gigahertz, 1.5 gigahertz, 2 gigahertz, 2.5 gigahertz, and 3 gigahertz. Well, that's all I had. Thanks for watching.